Right. Hello, people. Hello, I hope I'm audible. Yes. All right. So thanks for coming in today. I am Thameena. I'm a software engineer here at Equal Experts. I know you've all come here to hear Prashant talk about the internals of LLMs. But before that talk, I'm going to take the next 10 to 15 minutes of your time and I'm going to talk about a small project that I've built. And through this, I'll be talking about embeddings and cosine similarity. And hopefully, all these concepts will fit in very well into the next talk on LLMs. So let me first talk about the project I built. So what I have built here is called a semantic word ladder. So does anybody know what a normal word ladder is? When we hear the term word ladder, what comes into your mind? So this is what a word ladder looks like, a classic word ladder. You will have a source word, start word, and an end word. Here it's head and the end word is tail. And you get from head to tail by just changing one letter at a time. So from head, you get heel by changing the last letter D to L. And heel becomes teal, that becomes tall, and finally tail. So you're changing one character at a time or one letter at a time. Right? That's a classic word ladder. Now, what I have built here is slightly different. It's called a semantic word ladder, which means you still have a start word and an end word, but instead of changing one letter at a time, you will be changing the meaning slightly, step by step. So here I have my start word as heat and end word as sky, and I get from heat to sky by changing the meaning slightly. So heat becomes warm, warm becomes hot, hot becomes sunny, cloudy, clouds, and sky. So I'm forming a chain of words where the meanings are related and it finally becomes a sequence of words. That is called a semantic word ladder. So let me quickly show what my project looks like. So this is what I have. It's a very simple UI deployed on Hugging Face spaces. And it just has two inputs, the start word and the end word. So here I've given the start word as sleep and the end word as weather. And if I click on find semantic path, this is the path that is formed. Sleep becomes wake, sunrise, sunny, cloudy, rain, and weather. So we are moving through a small series of words. And the words just differ by small meaning or words used in similar context. Let's try a different word. Let's say laugh and maybe food. So this is what I have. This is a different ladder. Laugh, humor, comedy, entertaining, boring, tired, sleeping, morning, breakfast, and food. Maybe let's try two words that are already very similar to each other. Let's say we have hot and cold. There are already two words that are already similar. So the ladder that is formed is actually very short because hot, warm, and cold, they're already very similar words, right? So this is what a semantic word ladder looks like. And for the next couple of minutes, I am going to talk about few concepts that you need to understand to build something like this. Or in other words, I'm going to explain how sleep found its way to weather. So since this involves a lot of words, right, the very first thing I need is data set of words, right? So I've used a data set of 10,000 commonly used English words as the input. And after getting those data sets and loading that, the next thing I did was to convert those into embeddings. To explain embeddings better, let me take the analogy of GPS coordinates, right? So as you all know, every location on this map or planet can be represented as a coordinate of its longitude and latitude, basically an array of two numbers, where the number stands for the latitude and longitude, right? And if you take two coordinates, let's say Mumbai and Delhi, that is actually comparatively closer to each other, you will also notice that the coordinates or the values are actually close to each other, right? Because Mumbai has 19 and Delhi has 26. Similarly, the longitude is 77 and 72. So compared to other regions, the values in the array or the latitude and longitude values are close to each other. And if the values are close to each other, that means they actually fall physically close to each other on this planet, right? So similar to how we use GPS coordinates or an array of latitude and longitude to understand how close two locations are, we can use an array of such similar numbers to understand the meaning of words, and that is called an embedding. So mathematically, it is represented as an array of numbers. It's called vector in maths, and a vector, it looks like this. So if you can use an embedding model, there are different models out there to convert a word into an embedding. And let's say you convert king into an embedding, it will look something like this. It's just an array of numbers called a vector in Max. And the model I've used here is called All Mini LM L6V2. It's a very small model. And these models are trained on a lot of existing words so that it understands the meaning of these words. Now, a GPS coordinate has only 2 dimensions, and you can just represent it as just 2 numbers in the array, right? But here, the vectors or the embeddings that's generated, this array of numbers has, for this model, it's 384 dimensions, which means there would be 384 numbers in this array. And if you look at the numbers of king and queen here, for example, they are 2 words used in similar context, right? And if you look at the numbers that's generated, the numbers are actually close to each other as well. So if you try to represent this on a 2D graph, I know you can't plot a 384 dimensions on 2D space, but hypothetically, if you assume that it is just 2D and has only 2 coordinates, the graph would look something like this. So king and queen, 2 words used in similar context, will be close to each other. And let's say king and bicycle, 2 words that is not used in similar context, would be farther apart from each other if you plot it. So this is how it looks like, right? And this is what an embedding is, nothing but an array of numbers that actually contains the meaning of these words. So when you plot it, meanings with similar words will actually be adjacent to each other. So creating embeddings programmatically is pretty easy. I have a small snippet of my code here. This is written in Python to just explain how easy it is to create embeddings. So the very first thing I have done here is I have read the words dataset that I just mentioned, right? The dataset that has 10,000 words. It was stored as a text file, so I've just loaded that into code. And then I've used a library called sentence transformer. It is just a Python library to use embedding models. And I've passed in the name of my embedding model here, which is all mini LM L6V2. And just the next thing to do is just call the encode method on the model by passing in the words, the dataset input. That's it. And the output that is generated is a list of embeddings and an NumPy array of embeddings here. So let's say if I had 10,000 words in my initial data set, I will have a corresponding embedding for each of the words in the data set in my NumPy array. So the size of the NumPy array, the embeddings that's generated will also be 10,000. Okay, so that is how you create an embedding from Word. It's pretty simple and very straightforward. So now let's see what we have till now. We have loaded the dataset of 10,000 words, and then we have generated the embeddings of all those 10,000 words, right? Now this is a one-time operation, and now we have everything that we need to actually start creating the word ladder. So the next thing that we have for the word ladder is the start word, right? In this case, we had the example of sleep. So you take the word sleep, and you've already generated a lot of embeddings in the previous step, right? And that embedding will also have the embedding of sleep. So from those embeddings array, you pick the embedding of sleep. So now you have an array of numbers, which is the embedding of sleep. The next thing to form a word ladder is you have to find a word that is similar to sleep, right? Or in mathematical terms, you have to find a vector or an embedding or an array of numbers that has values similar to that of the embedding of sleep. Or in other words, we have to find similar embeddings, right? So we have to find embeddings or values of those vectors which are closer to the embedding of sleep. And how do we do that? And that is where the concept of cosine similarity comes into the picture. So let's say if we again try to plot these vectors in 2 dimensions, this is what it would look like. The first image out there, I have king and queen. And since they are 2 words used in similar context, the angle between them will be small. But if you look at king and bicycle, they are words not used in similar context. The angle between them will be larger, right? So to understand if vectors are actually similar, the idea is check if the angle between them is smaller. So if the angle is smaller, the words will actually be similar to each other, right? And mathematically, instead of calculating the angle, you can calculate the cos theta of these vectors. So if we have, say, 2 vectors A and B, the formula looks something like this. Cos theta equals A dot B divided by magnitude of A into magnitude of B. Now you have to first calculate dot product of these vectors and multiply their magnitudes.
Can I ask a question?
Yes, go ahead.
So this hi. So whatever we showed so far, like king, queen, it was a vector with single dimension kind of thing, correct?
Yeah, not single dimension. It has 384 dimensions. So
yes, 384 dimensions. Oh,
So
oh,
this is
that's how.
hypothetical. So I
Understood.
can't plot 384 dimensions in 2D. So
Understood.
assuming that I took just example of a two-dimensional space to explain this better. So instead of 384 dimensions, which means you'll have 384 numbers in the array, if we assume that this is only 2 dimensions, and if we have only 2 numbers in the array, and we try to plot it as x and y, this is what it would look like. But
Understood.
ideally, you can't do this because it has a lot more dimensions. So the model that I have used has only 384 dimensions. But if you look at any other models, right, there are OpenAI models that has more than 1,000 or 3,000 dimensions, which means there are 3,000 numbers in the array. So you can't really plot it on 2D. So I've just taken this example to explain the concept of cosine similarity better in 2D.
Just one thing.
Yeah.
Let's say we are taking two dimensions, king and queen. So are we treating king as x and queen as y? And then
No, so when I say x, y, they will have 2 coordinates, right? Let me go back. So the coordinates will look something like this. Let's say 1.5 and 4. These are just hypothetical values, not actual
Correct.
values. But you will have 2 dimensions, x and y, 2 coordinates. And you're just plotting them on a graph. That's it.
got it.
Yeah, thank you. Right. Coming back to the formula of cosine similarity, this is how you actually calculate the value of cosine similarity. Now a quick math refresher. Sorry, go ahead.
You are showing the embeddings for king and queen, right? So I see there are some 384
Yes.
dimensions, which is
Yes.
an array of
Yes.
some floats.
300, 800, 384 numbers, yeah.
Right. So how does the embedding model or the LLM model determine that? What is the base word like?
Yeah, so
for-
these models, they are actually trained on a lot of words.
Okay.
So when these are trained on a lot of words, they are trained such that each of these embeddings or vectors that is generated, they understand the meaning of those words as well.
Okay.
I think if I can keep that for the next talk, you might get your answer better. So maybe after Prashant's talk, we'll come back to your
Sure.
question as well. Yeah. Yes. Okay, so talking about cos theta. If you all remember what we learned in trigonometry, if the angle between two vectors is 0, which means if they are pointing in the same direction, cos 0 is 1. And if they are 90 degrees, cos 90 is 0. And cos 180, which means if they are in opposite direction, it is minus 1, right? So cos theta has a value between minus 1 and 1. And if you get the value of cos theta or cosine similarity as 1, that means the vectors are very similar. And if they are 0, which means they are not similar, minus 1 means they are in opposite directions or not similar at all. But ideally, when you calculate cosine similarity, you will get a value between 0 and 1. And if it's 1, that means those two words are very similar to each other. Now, this formula is pretty complicated, right? You first have to take the dot product, and then you have to divide them by the magnitude as well. But the thing about embeddings is that, so when I say magnitude here, that means the length of the vectors. So if you see here, king and queen has slightly shorter length than king. Similarly, bicycle has even shorter length than king, right? So that is, when I say magnitude, it means the length of the vector. And the thing about embeddings is that the length of the vector does not really matter. The meaning is actually embedded in the direction or the angle at which it is pointing to. Okay, so there is a way where we can actually ignore the magnitude of these vectors, or in other words, if we actually adjust the values of these vectors so that all of them have the same length, that process is called normalization of the vectors. So there is some mathematical calculations involved. You have to divide all of these vectors by their magnitudes. But that I'm not going into that depth, but that's called normalization, the process of adjusting the values of these vectors so that all of them point in the same direction. So if you normalize these three vectors, it will look something like this. King, queen, and bicycle, they have all the same length right now, but the angle between them has not changed. So they're still pointing in the same direction. So that means the meaning has not changed. The meaning is incorporated into the direction or the angle and not on the length. And that is called normalization. And if you actually normalize these vectors, then the formula for cosine similarity becomes even simpler. It's just A dot B now. You just have to figure out the dot product of these two vectors. That's it. You don't have to worry about the magnitude. So that is called normalization. You can actually simplify the formula of calculating the cosine similarity. So okay, now coming back to our example of sleep. Now I have the word sleep, I have its embedding. The next thing to figure out is words which are similar to sleep, right? Which means a brute force approach would be, I have my 10,000 words dataset. I would calculate the dot product or cosine similarity of sleep with every other word in the dataset. Now, this is just 10,000 words. This would work, but as the dataset grows, this is not going to scale very well. It's going to be an expensive operation to calculate the cosine similarity of every other word and then take the one with the largest cosine similarity. So what I have used here is a library called FAISS. It's Facebook AI Similarity Search. It's a library created by Meta for fast similarity search lookup. So what it does is, it indexes all the embeddings internally, and it uses dot product as well internally. So all that you have to do is call the library and say, hey, I have the word sleep, give me 3 words which are similar to sleep. And it would give you something like this. Again, this is examples. So if I ask FISS to give me words which are 3 words which are similar to sleep along with the cosine similarity, it will give you something like this. Wake, which has a similarity score of 0.82, nap 0.79, and dream 0.70. So as I mentioned, the cosine similarity values will range between 0 and 1, and 1 means most similar, right? So in this case, out of the 3 words that was returned, wake, which has a score of 0.82, is most similar to sleep. That is what this means. So you don't have to necessarily calculate the dot product yourself manually. You can just use this library as well, and that will actually give you words which are similar to the specific word that you have given. Now, let us see what we have till now. Yeah. So we took the word sleep. We took 3 of its neighbors. We got 3 neighbors from FISS library. We got dream, wake, and nap. And let's assume that I chose the word wake next, and then I repeat the same process. I choose 3 words. I got 3 words which are similar. And again, out of that 3 words, I choose 1. And I repeat this same process until I reach my target word, which is weather in this case. So this is what I'll be doing, right? And if you take a step back and look at this, this has now become a graph problem. So each of these words is a node in the graph. There are neighbors which are words similar to a word, and you have edges connecting a word to its neighbor word. And you have to find a path between sleep and weather, the start word and end word, which is just traversing 2 nodes in the graph and trying to find 2 paths in a graph, right? So this is basically boiled down to a graph problem now. And the next question is, what algorithm do you use to actually find a path from the start word to the end word? The whole problem boils down to that, the traversing a graph, right? And how do you decide, let's say you have 3 words, how do you decide which word to take next? Let's assume that you just decide to take the word with the highest similarity, in this case wake. But that might not always work. There's no guarantee that it will reach your target word. You could try a BFS approach, but you might also just end up going down a path that is not getting closer to your target word, right? So not all algorithms work in this case, but one algorithm that works here is called A-star search. So this is just another graph traversal algorithm, but it works very well in our use case. And how A-star search works is, at every step, it asks 2 questions. 1, how far have we come? And 2, how close is this to the target? Okay, so mathematically, it is represented as something like this. F of n equals g of n plus h of n, where f of n stands for how far we have come, or number of steps taken so far, and h of n is the distance to target, or how close this word is to the target word. So when I say the word close, in our context, it is the cosine similarity, right? If we have to figure out how close we are to a word, we calculate the cosine similarity. So in this example, let's say we have sleep, we have 3 neighbors, wake, nap, and dream, each with a cosine similarity score. What this algorithm would do is, it will actually calculate the f of n for each of these values. Now, this algorithm is designed such that it takes the least f of n at any given point of time. So when we calculate h of n, it's going to be the cosine similarity. So let's say wake, right? You have to calculate the cosine similarity of wake to a target word, which is weather. And let's say the value is 0.82. So I've just inverse the value 1 minus 0.82 because I need the least h of n value. So if we have to find f of n that is least, so I'm just taking h of n value that is very less. So I've just reversed it, 1 minus cosine similarity. And how A-star search works is, it keeps a priority queue and picks the one with the lowest f of n score. So at every point, it looks at all its neighbors, calculates the f of n score, adds them to the queue, picks the one with the lowest f of n, traverses that graph, again takes the neighbors of that particular node and it keeps adding to the priority queue. So at any point, let's say at any point in the graph, if one branch starts looking bad, that is if f of n score starts going up, that goes down in the priority queue. And any other node that it saw previously in a different branch that had a lower f of n score, that will get picked up and the path and this algorithm will traverse that path. So this is how A star works at a very high level. And this way it actually finds a good path to the target node without really getting stuck. So this is just another algorithm that you can use to actually solve this problem efficiently. And that is how you get from sleep to weather using embeddings, cosine similarity, and A star search. That's it, a very small project that I had built to kind of explain all these concepts well. Any questions? Yeah.
Yeah, since these words, every time it will give the 3 words. Let's say if you are taking 3 words.
Depends. So you can
Yeah.
actually decide how many words you actually want to put in.
Yeah, that distance remains the same. If you
Yes,
calculate
it will.
F1, then why can't we directly dump into one graph DB so that it will be same? It will be.
It depends. If you actually don't want to store it, you don't have to do it. So every time I'm giving different input words, right? So
Yeah.
my start word is different. So you could also do that, but I did not choose to do that here. I just decided to traverse it dynamically each time with the input and output word.
And that will take a lot of time, right? Every time, let's say, if 2 words are too far.
But even if you're asking why can't we pre-build a graph, right?
Yeah.
So still you have to traverse the graph.
That's the one-time effort.
But the start word and end word is going to change each time. So you still have to.
But that distance every time it's pre-calculated, right?
Yes, it is pre-calculated, but here let me go back. I did not talk about this earlier, but here I've given an input also, which is the number of neighbors that you have to consider each step. So I can actually keep changing the slider. So if I want to consider 5 words at a time or 6 words at a time, the number of neighbors that is chosen at each step, I can actually change this also. So at this point, the words that is chosen or the graph changes depending on this input as well.
Okay.
So I have 2 questions. One is related to the algorithm that you have showed us. So how is end word related? Because we started with the start word and then we are finding everything related to that and going in the node format. But how is end word related?
Yeah, so end word is related by this h of n function here. It's called a heuristic function. This actually checks how far, how close a word is to the end word. So if you take the word wake here, right, you are calculating the cosine similarity of wake to the end word weather. So let's say so here I have this column here, which is the cosine similarity to weather and not to sleep. So we are actually checking how close a word is to the target word by calculating the cosine similarity of that word to weather. So that actually tells you how close you are to reaching the target. So none of the other algorithms, or you could still have other algorithms do this, but this is just another efficient way where you're calculating the cosine similarity of that word to the target word.
Okay, and I understood all of this, but is there any other application of it where it is used like this semantic word ladder?
No, this is just a fun project that I
It's
built to
just a
just
fun project.
understand these concepts, that's all.
Okay.
Cool.
I have a few questions, but I'll keep those for last.
Sure, all right. We can take more questions after Prashant's talk as well. All right. Thank you.